So, well, so last video, we talked about, or at least I did, integrality. This is something we've sort of talked about, sort of in a loosey-goosey kind of way. So we made that a little bit more formal last time. And now, from the notes, it looks like I'm like maybe freaking out a little bit, doing something totally different, but I'm not. So my jump from integrality into this, we are going to see as a natural one because there's a connection between this and the notion of integrality. I'm not going to tell you what evaluation is yet. I'm going to tell you what evaluation domain is first, and then come back to what the notion of evaluation is. This is one of my favorite definitions for a domain. We say that R is a valuation domain. Well, domain, if it's an integral domain in the first place, if given A, B in R minus 0, A divides B, or B divides A. But that means if you pick two random non-zero elements in this domain, one of them has to divide the other. I know one kind of domain, large class like this, a field, right? Because if you pick any two elements, they're both invertible. So in fact, they both divide each other, right? But evaluation domain may be one of them in a certain sense bigger than the other. It's easy to show these are equivalent. For all so if you take any non-zero element of the quotient field, then omega or omega inverse is in R. So if you take any non-zero element of the quotient field, either it's already in the range or its reciprocal is, or both. So this is called evaluation domain, and at this point right now, you might want to, well, why is it called evaluation domain? What's this evaluation business? Well, we'll come to this soon. Here's an example. Here, how about some examples? Evaluation domains. Okay, I'm gonna take an easy one here. One, fields. Any fields automatically evaluation domain. But if you wanted an example that's not a field, we're gonna have to dig around a little bit, right? Because you know, the first example, every time I introduce a classical range, the first question is the integers one? And of course, here the answer is no. Because take 2 and 3, neither one of them divide the other. All right. So what else? How about any formal power series or in the field? That's field. Because one of the things that we've seen earlier in class is any I remember back when we talked about Euclidean domains a bit, we came to the conclusion that if you have a non-zero power series, f of x, this can be written as x to the n g of x, where n is at least 0. And G of 0 is not 0. So, and this is the big thing with the Euclidean algorithm. If G of 0 is not 0, what is the status of G of X in the formal power series ring? Must be a unit, right? Because a non-zero constant term is a unit if you're a field. So basically, when we did the Euclidean domain thing, we noticed that every element in F power S is not 0 is essentially up to a unit a power of X. And that meant the Euclidean algorithm was very easy. Take two elements, they have to be X to the N and X to the M. If N is less than or equal to M, it divides completely. And if not, then your quotient is 0 and your remainder is the smaller one. So in particular, zero, then then if N is less than or equal to M, G Xm G1 of X divides Xm G2 of X. And I won't break down the cases, of course. It's the other way around. It's the other division. So give me a pair of elements, one of them divides the other. Here's another example. So remember what this is. This is the set of fractions of A over B, where P does not divide B. So notice in this example right here, what's going on is, let me kind of prove the evaluation domain. We pick a random element A over B in here, right? And the only rule I have in B is not to do the plot. Well, A prime, B prime, pick them both, right? So B doesn't divide B prime play. What can I do? Well, I can write A over B as P to the M, A1 over B, and A prime over B prime as P to the N, A1 prime over B prime. We're here, so basically what I've done is I've pulled every factor of P out of these numerators that I can. And of course it could be even a 0. So now what we have is these fractions, both the top and the bottom, are relatively prime to P. So these are both units here. So it's the same kind of argument that we have here. Given any pair of elements, one of them divides the other. Whichever one has the smallest exponent on P divides the other. If it's a tie, they divide each other. Everybody okay? Now, just to show you that there's more in the zoo, can anybody give me another example of evaluation domain that is spiritually different from this, right? And what I mean by this is these two rings are certainly not isomorphic in general, right? However, what's going on in the valuation is essentially the same, right? In both cases, what you have is these are both principal ideal domains that have only one non-zero prime. Right here, it's X, and everything interesting is power of X times a unit. Here it's P, and everything interesting is a power of P times a unit. But interesting, I mean obviously. Can somebody give me a valuation domain that really is kind of different?
I was breaking, I was gonna say.
You're close. The problem is, the ring of all algebraic integers is an evaluation domain because you still got 2 and 3 in those, and neither one of them divides the other. Neither 2/3 nor 3/2 is the root of some mnemonic polynomial. But not a bad idea.
Is the power series ring over the p-adics also valuation?
No, because the p-adics are actually already one-dimensional. And so you take the power series ring and, well, here's the problem. For power series ring to be a valuation domain, then the coefficient ring has to be a field. Because otherwise you're going to have X in some non-unit of the original ring, and neither one of them will divide each other. Okay, how about this? I'm going to build 2 examples that are both different from each other. Take any field. Let's say yeah, I'm going to build this. First, I'm going to build this semi-group. What do I mean by this notation? By the way, I could have replaced R with Q, or actually, I could use any totally ordered forbidden group. So, what do I mean by this? Everybody's familiar with the old-fashioned polynomial ring, right? Your exponents come from the natural numbers, right? This is basically a generalization of polynomials. Now, what my exponents come from the real numbers. Actually, let me be the positive real numbers. And by positive, I mean non-negative. Right? But it's easier for me to write a plus greater than or equal to 0. So what this is called a monoid domain. This is all polynomials that you can build to the where alpha I lives in the field and Ri greater than or equal to 0 is. So it's sort of like polynomials, except now I'm allowing my exponents to be non-negative, right? So I've got exotic things like x to the 2/5 and x to the pi cubed over 17 and all kinds of crazy stuff like this, right? Yes.
Would that be R plus or real numbers? Plus?
Oh, yeah. Well, I think I've covered it here, right?
Oh.
Yeah, so any non-negative element. And of course, you can group. You can also assume when you write this out that all the powers are different, right? Because otherwise you could have just grouped them together, right? Now, this is an evaluation domain as written because you've got problems, right? If I give you, for example, let me give you an easy example. If I give you X and 1 plus X, right, and neither one of those divide each other, right? But what I can do is let M, my notation, I hope suggests this is going to be maximal ideal, is the set of let's call this R, such that f of 0 is not 0. So basically what I'm looking at is I'm looking at my new exotic polynomials that have a non-zero constant term. This is a multiplicatively closed set. right? Because if you multiply two things with a non-zero constant term, you get something with a non-zero constant term, and it's also saturated because the product of two of these things as a non-zero constant term, they both have to have that. And this is a maximal ideal. And the easiest way to see this is do the quotient map from R to R mod M, and you will see that the kernel, the kernel of this is precisely F, the set of all polynomials that have a non-zero constant term and is isomorphic to F, which is a field, so it's maximal ideal. Right. So what am I going to do now? Now what I'm going to do is I'm going to let V, suggested again for valuation domain, is R localized maximal ideal. Right. Now I'm going to do a little computation, and I hope convince you that this is indeed valuation domain. What does a typical element look like here? Well, it's a fraction. Numerator is one of these things, and the denominator is one of the things that's not the maximal ideal, so it's constant term. Now, the things with the non-zero constant terms are units in here, right? Because you've got one over there. So you can actually, up to associates, write an element in here that's not zero, it's just one of these polynomials. Because even if it's over something, just multiply by that denominator and it's going to be back to being a polynomial. So what does a typical polynomial look like? Well, X R1, R2. So alpha. And so this is what a typical element looks like, right? And I'm going to assume R1 is less than R2, less than Rn, right? And I'm also going to assume that R1 is bigger than 0. What do you suppose I'll make that last assumption that R1 is bigger than 0? Yeah, so if this is 0, and let me make another be technically correct. Let's assume the alpha i's are not 0, because if one of them was 0, I just wouldn't have written it, right? So this is a non-zero element here. So what happens if R1 is 0? Then this is just a unit, right? So what can I do? I've arranged these so they're increasing. So I can write this as x to the R1 x to the R2 minus R1 x and I'm hunky-dory here because all my exponents are positive, right? And this is x to the R1 times a unit. So any non-zero element of B is of form x to the R times a unit, with R greater than or equal to 0 and U a unit in B. Okay. Eric, you look quite disturbed. So what's
Oh,
that?
well, I'm just thinking about this, I'm thinking like, so like the valuation group is like R, like, it's like isomorphic.
That's the value group. That's right.
Whereas in the other cases, it's like discrete valuation.
That is exactly
so
right.
That's like the distinction.
I'm going to give you a bigger discrete valuation in a moment, as a matter of fact, but yeah, so basically What's different now is everybody comfortable with where we got here? That everything in here is not zero? Yes.
I guess I'm a little bit confused when you say you're trying to show B is valuation of A. It seems like you're just working with R. Like, well, and you have,
Right, because everything in V up to a unit is in R. Because a typical element of V is gonna look like R of X over some other, G of X, where G of X is in the maximal ideal. Or I'm sorry, not in the maximal ideal, right? So G of 0 is not 0. Correct?
so it is an M.
No, it's not an M, because M, yes, thank you. So this is, you guys should have yelled at me before. This is F0 equals 0. The stuff that I'm dividing out by is F of 0 is not 0. Yes, that's a mistake. So does that take the worry lines off your face?
I think so. So then,
So right, so anything
so
here.
then just like formal power series, it's everything in the denominator. Seems like it should already be a unit.
It is, right.
So
And
why do
that-
we need to localize if it's already a unit?
Well, because if you don't have that localization, then all of a sudden something in the original ring, something like 1 plus X is not a unit until you make it a unit, right? And so if 1 plus X is not a unit here, then it's not a valuation domain, because for example, 1 plus X and X, neither one of them divide each other. But when you make that 1 plus X a unit, now the 1 plus X divides X.
Okay, and the reason 1 plus X is not a unit is because it's not formal power series, it's just finite.
Well, it's not, it's maximal ideal, so I allow it to be a denominator. Right, this maximal ideal consists of every one of these generalized polynomials. When I plug in 0, I get 0. If you look at 1 plus X is not in here. Right, because we plug in 0, you get 1, which means that 1 plus X is allowed to be a denominator here. So now I've got R of X over 1 plus X. And what I did over here is I said, well, let's just think about 1 plus X, because this thing up to a unit is Rx. Right, because I can just hit it with that unit. So, and that's why I say up to a unit, anything looks like this. You could also have encoded into that U, you could also have the 1 plus X in the denominator.
So like module theoretically, this is like a direct sum indexed by the positive real number, whereas like a power series would be like a direct product.
As a module over what?
Over F, the field F.
Like it's a vector space over F, yeah. It would be indexed by the positive real.
Whereas like just like maybe to make this more clear, like the power series would be like a direct product indexed like over.
Yeah, so if you look at just general formal power series, and you consider that a module over the coefficient ring, then that is a direct product of whatever the coefficient ring. This one's a direct sum over a bigger index set, right? And the difference is these are all finite sums, whereas power series I can go bananas. Right? Everybody okay with it? Yes.
Sorry, one more thing. So last time when we had like a formal power series, all the stuff with F of 0 not equal 0 was already automatically a unit.
Yeah, that's right.
If we change this to a formal power series, would that take away the need for localization because they'd already be units? For the same reason as before.
I don't know the answer to your question, because I have to figure out what exactly I mean by formal power series in this situation. Are you going to allow me to put uncountably many things in the power series?
That's what I had in mind, but I don't know if that, like, all the details work. I guess, yeah, I'd have to think about the details, think about how it would work. That's what I had in mind.
Right.
Because right there, you just have a finite sum allowed.
Yeah, that's right. And that's the way I'm going to keep it now, because for me to answer your question properly, I need to think about what the rules are first. Okay, other questions?
What's the dimension of the as evaluation or at?
So if you're talking about problem dimensions, one. So. To add to this point, in fact, maybe I'll show that that's true. Um. Notice that, in the ideal generated by right, if you notice that generated by every positive power of X is maximal ideal. And it's a fairly simple exercise to show that there is no ideal that's properly, let me rephrase, there's no prime ideal that's properly contained between here and here. Because in fact, in this case, I'll call this N, so I don't abuse my notation too much. If I is an ideal of V, then the radical of I is equal to N. And you can use that. So in other words, what we're saying is anything that's non-zero in here, this is the radical of that ideal. So we're gonna see this later that, or we've actually seen that the radical of an ideal is the intersection of all primes that contain it. So there's basically only one non-zero prime ideal because of the statement.
So. Things got a lot of generators, huh?
That's right, that's right. I mean, it can't even be countably generated, right? Because the problem is, if you make a list, there's always just one half of the smallest one, right? And you can't even do it for countable many, right? What do you think about that? No, I guess you could, because you could generate by 1/n for all n, couldn't you? Because no matter how small the real is, you can always be smaller than that. I take that back, it can be countably generated. But you can make the set bigger, so it doesn't have to be. Let me give you one more example. I promise you one that's a little bit different. Again, we'll start with the field. This one's my favorites. Yeah. This one right here is actually, let me point out, is a subring of fxy. A polynomial ring in two variables. Basically, what I've done is I've taken just the ordinary polynomial in the variable x, and I've just thrown in all these rational functions: y over x squared, y over x cubed, etc., etc. Forever. Yeah, you have to go forever. Now, here's what I want to do here is I want to localize at what does a typical element of this look like? Well, again, it's going to be a finite sum. It's a little hard to wrap your head around, but it's one way that you can certainly write it is you can write it as, well, a typical element is sums of products of these monomials. Sum of products. Monomials. Form.
Did the containment go the other way?
Oh, yeah. Actually, I meant to write, this is what I meant by it, it's in rational functions, next slide. There we go. Right, so this is a subring for rational functions. So a typical element just is a linear combination over the field F of certain monomials, right? So a typical element looks like alpha 0 plus alpha 1 M1 plus alpha K MK, where alpha I is in the field and MI is a monomial. And what form do these monomials take? Well, certainly that. And certainly that. Right? And then it gets more exotic. You can certainly have powers of this. And in fact, a typical monomial multiplying these together probably looks like this, right? Let me see if we can use this to capture a general form. So allowed monomials here. Uh, uh, right. And I think I want to run this set. This is great. Excellent. So a greater than or equal to 0. So if you see kind of a naked power of X, like there's no Y's kicking around it, then this has to be 0 or greater, right? What's the restriction on the other one? Well, for example, if M is 0, what restriction do we have on N?
It also has to be 0.
It also has to be 0, right? You can't have just a 1 over X by itself. All right, okay. What happens if N equals 0, if M equals 0, and if M is greater than or equal to 1, then what restriction do we have on X?
Yeah, it's greater than or equal to 0,
Hmm?
because you have y into the n divided by 1.
Well, that's true, but N could also be negative. Right, because that's just bring the positive powers. Right. So for example, if M is 1, this could be Y over X to the 1 billion, because it's way after there. It could also be Y over X to the negative 1 million, because that's just X to the 1 million times Y, which is both in there. Right. Everybody okay with it? Now, let me point out something. What happens if you have let me point out that this is x to the 200 comes 1 plus y over x to the 202. And notice this is still a legal element. Right? What happens if you have something like this? Sort of the largest common factor you can pull out of this. Actually, it turns out these three should have something large you can pull out.
Y squared over X squared.
Yeah. that's- This one leaves y over x squared, which is a legal element. This leaves 1. This leaves y to the 4th, and now I don't really care about the x, so this should be x to the 5. Or 5, what I pull out squared, yeah, this should be a cube. There we go.
The one,
Y cubed, x 4th, y squared, x squared. Y. Yeah, I got the number wrong again. This is going to be 5. There we go. Right up here. So in general. I'm gonna do something similar to what I did last time. Let M be the set of A0 plus A1 M1 AK MK, where A0 alpha 0 is 0. So it's all the sums of these monomials where you've got the constant term 0. You don't have anything in the field. Since there's x in the denominator, I hesitate to say plugging 0 gets you 0, right? This is a maximal ideal, and it's fairly easy to see that when you have, if I call this original ring R, that R mod M is isomorphic to F. So again, this is a maximal. And if you look at R localized M, this is a valuation. I'm going to take you through kind of a similar argument that we did before. And I'm going to do things this way. Alpha 0. K, K. Well, actually, let's do this way. Say beta 1. See, this is going to be the stuff with y's in it. So beta 1, y, S1, x, M1 plus beta L, Y, S, L, X, and L. And I'm going to write this in such a way that T1, okay, and S1, S2, SL. So I'm gonna write this in a special way. Increasing exponents on the X. Non-decreasing exponents on the Y's, and I'm gonna spread this out a little bit more. Can anybody guess what I'm thinking? I love this kind of questions, don't you? Anybody know how I'm gonna spread this a little bit more? And if SI equals SI plus 1 equals SI plus J. How do you, anybody want to guess how to rearrange it?
And all the and I's have to be included.
Right, and how am I gonna do it? Oh, in increasing order? Then. Range. So, N1, N2, NK. Actually, let me change, I need to get my indices right, I plus 1, I plus J. So if I have sequential ties on the Y, so the Y's are going up. And whenever I hit a plateau where all the Y's are the same, I arrange those in increasing powers of the X, right? And there's a reason I do this, because basically, when I come full circle on this, basically what I'm doing is I'm making the valuations in the appropriate order. So let me point out that if alpha 0 is a unit, then let me call this B, the bill, then B is a unit. Alpha 0 is not zero, so we need, then B is a unit without the E on there. In the first case, if alpha 0 equals 0, and alpha 1 is not 0, and without loss of generality, I'm gonna take alpha 1 and not be 0 and not some other alpha, because otherwise I just re-index them. Notice that I can do this. This is B equals X to the T1 comes alpha 1 all the way up to alpha K, PK minus T1. And this is all hunky dory because of all the powers of the X's. That should be X. There should be an X here. And I can keep, because the Y's are positive here, I can, any power of X is acceptable with a positive power of Y, right? If you've got a positive power of Y, you can take your powers of X to be positive, negative, so I can keep pulling stuff out. So this is going to be beta 1, YS1, X to the N1 minus T1 plus beta, whatever the end game was, L, Y to the SL, X to the NL minus T1. And notice this piece is a unit. So in the first case, the whole shebang is a unit. In the second case, this is X to the T1 becomes a unit. And what happens in the last case? Well, the last case is, now let's assume alpha I equals 0 for all I, And without loss of generality, we'll assume that beta one is not zero. Because some of these betas have to be non-zero, because I'm looking at non-zero elements, so. Now, notice that I can pull out. So now my element is B is beta one Y S1 N X M1 plus beta L Y SL X NL. And notice I can pull this whole thing out of here. This is Y S1 X N1 beta 1 plus beta 2 Y S2 minus S1 X N2 minus N1 3 minus S1 N3 minus N1 all the way up to beta L Y to the SL minus S1 X to the NL minus N1. There we go. Now, what I want to convince you of is this works. This is an element. So beta 1 is clearly R, right? What's the power of Y? The power of Y, if any of these exponents is positive, I don't care anymore what the power of X is, because coupled with any positive power of Y, you can get any power of X. What happens, you say cheerfully, if S1, S2 minus S1 is 0, right? Well, now what's happened is you're in this case. And so let's suppose that S2 minus S1 0, so S1 and S2 are the same thing. Then by the way I arrange this, this means that what, N2 or N1 is less than N2 strictly, right? So N2 minus N1 is positive, so it's a positive power of X and it's all hunky-dory. So this works too. So now in this case, what we have is Y to the S1, X to the N1 times a unit. So fantastic. What I've basically shown you with all these cases is this is valuation domain, because up to a unit in V, I've got three kinds of things. Units themselves, things that are a power of X times a unit, right? And if I throw in 0, that'll subsume the previous case. Or things with a positive power of Y times some random power of X times a unit. Right? So any two things, one of them divides the other. If I compare two powers of X, whoever has the smaller power divides the other. If I compare a power of X and one of these things, this automatically divides this, automatically. And if I compare two of these, right, Y to the S, X to the A, Y to the T, S to the B, or X to the B, which one divides the other? Well, whichever has the smaller Y divides the other. What if it's a tie? If it's a tie, whichever one has the smaller B is the one that wins that division game. All right. This is a valuation domain. It is also, some of you that like number theory might not have heard this terminology, but this is usually called discrete valuation domain, but it's not in the theory. It actually has value group copies, not just one. And we'll talk about what all that means later. But this one's different from the other ones also because if you look in this valuation domain V, if you look at its prime ideals, you get 0. And the maximum ideal is actually generated by X. Because X divides every freaking thing. And then you've got this intermediate prime. It consists of all the stuff that's got Y's in it. Right? So if you stack the primes. The ideal generator, y over x squared, y over x cubed, forever. This is the ideal that has all the y's in it. This probably defies your intuition a little bit, right? Because I don't know about you, and this tends to be true in Noetherian rings, that as you stack your ideals higher, you think you need more generators, right? But the opposite is true here. The middle prime is not finitely generated. The maximum ideal is principal. Matter of fact. So there's some examples I've beaten to death. We'll talk more about this next time. Any questions? Any questions?
Do you think of any other mentioned two valuation domains?
Oh, yeah. In fact, if you take any two totally ordered abelian groups, you're going to order them lexicographically and build a valuation domain for that. I have a copy of Q and a copy of R, right? I can do all kinds of crazy stuff with it. Others? All right, well,
What are you ordering that, right?
well, so it turns out that what you have to have for the valuation domain to work is you have to have a totally ordered abelian group. So if you do something like take two copies of D and do the product order, that's never going to make you a valuation domain. What's going on here, and I'm glad that you're ahead of the curve here, because I'm going to talk about these groups in a moment, or well, not today, but this is two copies of Z, but they're ordered lexicographically. If you order them in the product order, what will happen is you'll have two elements that aren't comparable anymore. Right? So, others. All right, well, we'll catch you all on the flip side then.